In this video, I'm going to go through review 2 in the polynomials unit, and again, if there's a specific question you want help with, just go to the description and click on whatever question you need help with. So for number 1, choose true or false for each statement about the function f of x. The first one says true or false, f of x has x-intercepts at 1 and 7. Well, remember to find x-intercepts if it's already factored, this is in root form right here. We could just split it off and set each of those factors equal to 0. Now, of course, 4 is never equal to 0, but when x plus 1 equals 0, if I subtract 1 on both sides, I find negative 1 is the solution to that, and when x minus 7 equals 0, I find x equals 7 is the solution to that. So really, there are x-intercepts at negative 1 and positive 7, not positive 1 here, so I'd say that one's false. B says true or false, f of x has a y-intercept at y equals negative 28. Remember to find the y-intercept when you're on the y-axis, wherever you are there, that x value is equal to 0 because you haven't moved left or right. So anytime you're looking for a y-intercept, you could just take your function and plug in 0 and see what you get. So I would always recommend plugging this straight into the calculator and having it simplify for you. But just for the sake of argument, 0 plus 1 is 1, 0 minus 7 is negative 7, so 1 times negative 7 times 4 is in fact negative 28. So that checks out. For C, the end behavior can be described as down-up. So as x goes to negative infinity, f of x goes to negative infinity, and as x goes to infinity, f of x goes to positive infinity. Well, let's think about, the degree of this function. When I solved it, I got 2 roots, which means it must be of degree 2. So there's 2 things you need to consider when you're looking at end behavior. It's the degree, whether it's even or odd, and the sign of the leading coefficient. Now the leading coefficient is positive here. I'm going to erase some of my work. And I noticed that it's an even degree. So if you think about just a regular quadratic, that's either going to look like this, where it goes up on both ends, or it's going to look like this, where it goes down on both ends. Since my leading coefficient is positive, it's going to open upward, so my end behavior is up on both sides. So I would say this one's false, because it should be up, up. And for D, f of x has an absolute minimum. Well, even if you just take a look at my rough sketch of the end behavior here, this should have a bottoming out point where that's the lowest point that my graph goes because it's opening upward. So I would say that one's true. And just to double check, I would graph that in your calculator and just check to see if there's a lowest point on the graph. For number 2, it says to answer the questions about this polynomial below. So label the relative maxima A and the relative minima B. Maxima is just plural for maximums, and minima is just plural for minimums. So I notice this is the highest point over here, and this is the highest point over here. So relative to the points around it, those 2 points would be considered maximums because they're turning points. And there is a relative minimum right here because that's a turning point as well, but it goes from decreasing back to increasing. So fill in the correct blank below. There is an absolute minimum of, well, hold on a minute. This graph looks like it's going down forever, right? So I could always pick a point that's lower and lower and lower on this graph. So there is no absolute minimum in this case. So that is not applicable. But there is an absolute maximum, right? If I'm looking and I'm scanning up on my graph, there is a highest point that I reach. And it's that A right there, right? Because this A is a lot smaller, but this is the highest point on my graph. And that occurs at a y value of 11, 12, 13. So notice when I list the maximum, I only talked about the y value there. Part C says, is the multiplicity of the root x equals 0 even or odd? Well, I'm looking at x equals 0, and I'm noticing at x equals 0, there's a bounce. Right, so what do I mean by a bounce? I mean that if you're looking at the axes, as it's approaching the x-axis, it touches it, but then it turns around in the other direction so that it doesn't actually pass through. That's what I consider a bounce. Anytime you have a bounce, that is always an even multiplicity, whether it's a double root or a quadruple root. Usually in our cases, they will just be double roots. So now if we use that information to consider the degree of the polynomial, I want to look at all of those x-intercepts. This x-intercept right here has a multiplicity of 1 because it passes straight through the x-axis. We already talked about this one right here that has a multiplicity of 2. And again, this passes straight through. It comes towards the axis and then continues on the other side of the axis. So again, that's a pass. I'm going to consider that to be a multiplicity of 1 because it passes through the axis. So I've got 1 plus 2 plus 1. The polynomial could be degree 4. For part E, it's asking for the end behavior, so I need to look at these two arrows right here. So as x approaches infinity, that means as I move to the right in my graph, what happens to my y values? Well, notice that, this says as I move to the right, and I'm looking at my rightmost arrow, and it looks like it's going down forever, so those y values are getting more and more negative. So I'm going to say that g of x approaches negative infinity. And as x approaches negative infinity, so remember the negative numbers are on the left side of the y-axis, so this is as you're moving more and more left on your graph, what's happening to the y values? Well, again, they're going down, so I'm going to say they're approaching negative infinity. Right? If one of these sides had went up, then I would say one of these approaches positive infinity, but here they're both going down. And that makes sense because this is an even function, so the end behavior should either be up on both sides or down on both sides. Number 3. Given the graph of f of x below, what is a possible degree of f of x? Well, if I'm considering the degree, I need to consider the number of zeros or the number of roots, right? So I look at that x-intercept and I look at that x-intercept, and we do the same discussion we had before. Well, I've got a bounce here because it approaches the axis, hits it, and then turns away again. So that has an even multiplicity, but just to simplify our work, I'll say that it has a multiplicity of 2, because we really don't know whether that's a fourth root or a sixth root, so I'm going to say that it just has a multiplicity of 2 there. And again, that passes through the x-axis, so that just has a multiplicity of 1. If I add those multiplicities together, I get what my degree should be. So when I solve whatever equation this is and set it equal to 0, I should get 3 solutions out of that: 1, 1, and 2. Number 4. Given the following information for n of x, sketch the graph of the polynomial. So let's go through this piece by piece. The first bullet says f of x is greater than or equal to 0 for all values of x. Well, that's a lot to take in right there. Well, f of x values are kind of like y values, right? They're the same thing. So this is telling you really y is greater than or equal to 0. What does that mean? You got to think about numbers that are greater than 0, right? 2, 4, 6, 8, 1, 2. Any numbers that are positive are greater than 0, and then 0 is equal to 0. So this piece of information is just telling you that y is positive, or in the case that it hits the x-axis, 0. Ooh, that's not how you spell 0. 0, right? So when I see my graph, it should all lie above the x-axis, because otherwise, down here would be negative y values. So keep that in mind as you're going to graph this. Now, a is greater than 0. That's telling you your leading coefficient is positive. And that's going to help you figure out the degree if you're given the end behavior, which we are in the next bullet. So as x goes to negative infinity, again, that's as I move to the left in my graph, n of x approaches positive infinity. And my positive numbers go upwards, so my graph must be going up on the left side here. Let me give myself a little bit more room for this one. So I'm going up on this side right here. And as x approaches infinity, so as I move to the right, n of x approaches positive infinity as well. So it still goes up on this side as well. So I just have those arrows there to guide me when I sketch so I don't forget. Those might not be my actual arrows when I finish sketching this. So it has x-intercepts at 3 and negative 5. So let's see, 1, 2, 3, 4, 5. This one right there. And 1, 2, 3 right there. I think that's enough information to sketch this now, but you might be considering, well, Is it going to pass through these roots, or is it going to bounce at these roots? Well, let's consider one thing, right? If I pass through, all of a sudden, this is the danger zone. I can't have that right down there because that's below the x-axis. Those would violate my positive y value rule. So it must be the case that at this 0 I bounce off. And I don't necessarily know what my y-intercept is, so it could be anywhere. And same deal here. I can't go through, otherwise I would have negative y value, so I'm just going to bounce off again. So if we're looking at this and we're just trying to analyze a little bit further, well, what could be the degree here? I would claim that this could be of degree 4, because this is a double root right there, and that's a double root right there too. So just some things to be thinking about. For number 5, it asks us to factor completely. Now, this is 2 terms, so it's either a difference of 2 squares or one of those SOAP problems, and it's definitely not a difference because it's a plus sign. So I'm thinking this might be one of those sum or difference of cube problems. So if you don't remember the formula for the sum of cubes, right, that's a cubed plus b cubed, that factors into the first thing plus the second thing, times the first thing squared, minus the first thing times the second thing, plus the second thing squared. And the way I get this formula is by looking at the signs, right? The sign's positive, so my first sign should be the same as what I started with. My next sign should be opposite, and the last one is always positive. That's where I get that SOAP acronym from. So let's use that to factor this guy. The first thing you do is you need to figure out what 2 things are you cubing in the first place. Well, the second one's pretty easy, right? If you're not sure what you cube to get 27, just try a couple numbers. It ends up being 3. Now, if you cube 2, you get 8, but if you consider there's a variable component here, I would need to cube 2x to get 8x cubed. So now that I know what my 2 things are, I would consider this guy right here, let me see, to be my a, and this guy right here to be my b. So when I substitute into the formula, those are the pieces I'm going to use. So 2x plus 3 times 2x squared minus, I multiply a and b, so 2x times 3 is 6x, plus b squared or 3 squared, which is just 9. Now this is looking pretty ugly right here, so I'm just going to clean up 2x squared. If I square the 2, I get 4. If I square the x, I get x squared. And this would be the fully factored form of the sum of 2 cubes. Number 6. Find the roots of the following polynomial. Okay, so let's see. I'm going to set it equal to 0, and I'm going to solve that equation. So they don't give us a factor or anything to start with here, so I'm thinking this has to be factorable, otherwise I'd really have no way to do this. And if I'm seeing 4 terms, I should be thinking to myself, let's try grouping. So for my first 2, I notice they have an x squared in common, and I'd be left with an x and a plus 3. And to check yourself, just do a little bit of distribution in your head. Make sure you get x cubed plus 3x squared to save yourself any mental hassle later. And from 16 and 48, I'm hoping that there's a GCF of 16 so that I could just get x in my parentheses here, and they are both divisible by 16. When you do 48 divided by 16, you do get 3. And you should be happy about that because factor by grouping only works, right, if these 2 sets of parentheses are the same. Because I can think of that x plus 3 as a GCF that I could factor out of both of them, and the x squared plus 16 as my leftovers, right? So now I've got my 2 factors here. I scan through it just to see if there's any more factoring I could do. Sometimes there is, sometimes there isn't. I'm noticing that this is not a difference of 2 squares because there's a plus sign between them. So this is as far as I can go in terms of factoring. So I split it off and I set each of my factors equal to 0. Keep in mind, if the degree of this function was 3, because that's the highest exponent I see there, I should have 3 roots when I solve this. So if you don't, you must have missed a solution somewhere. I'm going to subtract 3 on both sides, get x equals negative 3. That's one of my roots. And I'm going to subtract 16 to get x squared equals negative 16. And here's the easiest place to forget something. When I take a square root on both sides, I get x equals the square root of negative 16 is 4i, but you need to consider that when you're solving this quadratic, you should have two solutions. So x is equal to plus or minus 4i. So here are your roots. Negative 3, negative 4i, and positive 4i. So while these are your roots, they're not necessarily your x-intercepts, because if I'm thinking about imaginary numbers, I don't plot those on the x-axis, right? I only plot real numbers there. So if I'm looking through here, and I want to know how many x-intercepts there are, well, there's only one, and it's the only real number I got for my roots. It's that negative 3 down there. So my x-intercept is just negative 3. There's only one of them. Number 7. The graph of the function p of x is sketched below. Which equation could represent p of x? So if I'm being honest, this is a multiple choice question. It'd probably be easiest to just slap all these in your calculator and see which one looks like this. But just for the sake of argument, let's do a little bit of analysis here. That 0 right there is negative 3. That 0 right there is 2, and that one right there is 3. So the corresponding factors to each of those roots, for negative 3 would be x plus 3, because if I set x plus 3 equal to 0, I would get negative 3. My corresponding root for 2 would be x minus 2, and my corresponding root for 3 would be x minus 3. A quick trick is that you could just flip the sign of whatever your root is. So I'm scanning through these, and I'm looking to see which one has these factors. And if you factor x squared minus 9, it factors into x plus 3, x minus 3, a difference of two squares, times x minus 2, which, ding, 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 are the exact factors that we need for this polynomial here. And notice that they're all to the first power, because all three of those x-intercepts pass straight through the axis. There's no bounce where they touch the axis and then turn around. So they all go straight through, so they're all of a multiplicity of 1. For number 8, algebraically write the equation of the polynomial graph below. So in order to write the equation, you need two things. You need the roots, and you need some other point on your graph that is not one of those roots. So I notice I've got these roots right here, negative 6 and 8, but they both have a multiplicity of 2 because they bounce off the axes. So really, my roots are negative 6, and 8, and 8, because they have a multiplicity of 2 because I see bounces there. Now, there's two ways you could write that in your equation, and we're going to talk about that in a minute. Now, let's see. Normally, I try to get the y-intercept, but I'm really not sure what that point is right there. But I see a clear point right over here that has an x value of negative 8 and a y value of 1,000. So make sure you are careful with those axes. They're not always scaled by the same amount, so make sure you're being careful if you're picking a number in between any of the boxes. So the point I'm going to use is negative 8, 1,000. And I'm going to write the equation by using root form. Now, this is degree 4 because there's 2 bounces, so there should be 4 roots altogether. So my root form should look something like this, right? If it was quadratic, it would have 2. If it was a cubic, it would have 3, but since this is a quartic or a 4th degree, it will have 4 roots. And the only piece of information we don't have yet is a. We have information that we could plug in for the roots. That's going to be right here. And we have information we could plug in for x and y. That's what we grab that point for. So we can make y equal to 1,000. I don't know what a is, but I could substitute in negative x everywhere I see an x. Let's consider what these roots are, right? So if I'm subtracting negative 6, that becomes plus 6. And again, if I'm subtracting negative 6, it becomes plus 6. X is still negative 8, minus 8, negative 8, minus 8. Now, at this point, if you've substituted in everything correctly, I don't expect you to be doing this by hand, and I don't expect you to do it piece by piece by piece. Slap all of this together right into your calculator. Get out a number and keep going from there. And when I did that, I got 1024, and if I divide that out on both sides, 1000 divided by 1024 actually reduces a little bit. So you're left with your leading coefficient is 125 over 128. And that's a piece of it, right? You're almost done at this point. You just need to substitute that back into the root form equation we started with. So let's take a look at that. What would this look like if I put all my pieces in? We're always going to have y equals, and we're always going to have x in our equations. We just need to replace the roots and the leading coefficient. So the leading coefficient we calculated, and my roots I already know, right? It's x plus 6 times x minus 8 times x minus 8. Now, if you don't want to write these all out, you don't have to. And even in this calculation step, you don't have to write them all out if you recognize that you've got two factors that are the same and two factors that are the same. This is what we mean when we say they have a multiplicity of 2. It's that they appear twice in your equation. So the way that I'm going to clean that up a little bit is just square them both, right? So x plus 6 squared times x minus 8 squared. You don't have to square both of them. Either of these equations are okay, but I think this one looks a little bit cleaner. And for the last one, number 9. If p of x is equal to that, and p of 1 equals negative 18, and p of negative 1 equals 0, algebraically find the value of k. Okay, there's a lot to unpack here, right? They give us these two pieces of information, and to find k, we could actually use either of them. It doesn't matter. This is telling me when I plug in 1 for x, I should get out negative 18 as an output. So it all should be equal to negative 18. Or when I plug in negative 1, I get out 0 as an output. Doesn't matter which point you choose. I'm going to choose this point right here. So I'm going to plug in 1, so 1 to the 4th, plus I don't know what k is. I'm solving for that coefficient. 1 cubed minus 2 times 1 squared minus 12 times 1 minus 8. And when I plug that in, this piece tells me it should be equal to negative 18. And we're going to find a k value that makes that true. So again, there are lots of places to go wrong when you're doing these calculations. So my recommendation, even with something as simple as 1, is to just take all of that good stuff and just type it into your calculator and see what it simplifies to. Because there's just a lot of room for error in these calculation problems. And when I do that, k times 1 cubed is just k. And notice I didn't type in the k term because I know that's a variable and that's what I'm looking for. So I just typed in everything else. Is minus 21 equals negative 18. And when I add 21 to both sides, I get k equals 3. And you would get the exact same result if you plugged in negative 1. It's just that sometimes when we plug in negative numbers, a lot more can go wrong. So B says algebraically find all the factors of p of x. So I know what p of x is, right? I've solved for that coefficient. It's just x to the 4th now plus 3x cubed minus 2x squared minus 12x minus 8. But the problem is, in order to find the factors, this is one of those ones where we set up a reverse tabular and we do the division for it. But I don't know what my divisor is yet. So you need to recognize that this piece of information right here is very telling. Think about, this is telling you x equals negative 1 is a root. Because when you plug it into your equation, it makes it equal to 0, right? That's the definition of a root. The corresponding factor to x minus 1 is x plus 1. So x plus 1 must be a factor of p of x. So the reason behind that is that if I set x plus 1 equal to 0, I would get negative 1. So this piece of information is the exact same if it was written x plus 1 is a factor of p of x. And if it's a factor, then when I do my division, my remainder should be 0. So I'm going to set that up right here. Remember that that dividend goes along the diagonals. That's going to be what our diagonals should sum to, and we're going to use that to help us find the quotient. The first thing I do is start in the upper left box, put x to the fourth there. I ask myself, what would I multiply x by to get x to the fourth, and it's x cubed. Then I do my multiplication. X cubed times 1 is x cubed. Then I look along the diagonal. They should add to 3x cubed. I already have one of them, so I need 2 more. And I would have to multiply x by 2x squared to get 2x cubed. 2x squared times 1 is 2x squared. And to get this diagonal to add to negative 2x, you could do negative 2 minus 2 just to get negative 4x squared. And always just do the sum to just make sure those diagonals add up. Again, minus 4x times x would get me minus 4x squared. Minus 4x times 1 is minus 4x. And to get this diagonal to add to negative 12, this would have to be negative 8x. So negative 8 times x is negative 8x. Negative 8 times 1 is negative 8. Okay, it worked out. If that bottom box does not match, you must have made a mistake somewhere. So either you picked the wrong factor here, or you made some arithmetic error in your division. So just keep that in mind. These always work out so that there is no remainder. So I could use that information to take a look at my divisor and my quotient and multiply them to get p of x, right? Because multiplication is the opposite of division. So I'm doing this so that I'm able to rewrite p of x as a product of two things, x plus 1 and x cubed plus 2x squared minus 4x minus 8. Now it said algebraically find all of the factors. I think there's more factoring that I could do here. That's 4 terms, so I'm going to start grouping that. I could pull out an x squared from the first two to be left with x plus 2. And I could pull out a minus 4 from the next two to again be left with x plus 2. I could factor out an x plus 2 and rewrite my leftovers, x squared minus 4. But wait, there's more, x squared minus 4. To me, that looks like a difference of 2 squares. So I'm just going to bring down that x plus 2. And x squared minus 4 would factor into x plus 2 times x minus 2. And of course, we have that x plus 1 still hanging out here. So these are all of my factors of p of x. There should be 4 linear factors because it's of degree 4. So notice I didn't go a step further and solve for my roots because they asked me for just my factors. But if I look over at part C, they are asking me for my zeros. So I'm just going to take this guy over here, and we're going to find the zeros now. That part's pretty easy once you've done all the hard work. It's just a matter of setting it equal to 0 and setting each piece equal to 0. So if you split it off, you should recognize that you get 4 roots. You should get x equals negative 1, x equals negative 2, x equals negative 2, and x equals 2. So just to reflect, if for some reason you needed to sketch this polynomial, there would be a pass at negative 1 because it only appears once, a pass at 2, but at negative 2 there must be a bounce because it has a multiplicity of 2. So just to wrap up, we started by solving for k using either of the points they give us by plugging in an x value and setting it equal to the output. And for part B to find the factors, we needed to find one factor to start with and use it to do reverse tabular to divide to multiply the divisor and the quotient. From there, we divided the quotient even further, and then we set each piece equal to 0 to find the zeros.